Okay, so thanks very much for the invitation to lecture here. I really like the subject of the algebras, and especially their geometric origin. So what I wanted to do was, in this introductory lecture, is give you some basic notions of differential geometry. I already sent some notes that I sent to Peter. I'm not sure if you got the link or not. Just sort of skeleton notes of the language that I kind of hope you'll speak by now. But I will remind you of some of these things as we go along. But the idea is essentially to, once we get the language out of the way, then I'll give you some example of the algebras of geometric origin. Patricia had a request of me to discuss symplectic and Poisson geometry, so I'll briefly do that at some point. I want to pay particular attention to one Lie algebra that is associated with every Riemannian manifold, namely the Lie algebra of isometries, and in particular the algebraic structure that it has, which is not just any Lie algebra, but it has a very particular structure. And the idea is because later in the more advanced lectures, I'm going to speak about the geometric construction of some Lie superalgebras. And if you see that for the first time, it does appear a little bit strange, a little bit abstract. But hopefully, if you have seen the Lie algebras of isometries in that light, then hopefully the super case will just be a natural extension and not something totally different. And because of the super thing, of course, I will have to tell you a little bit about spin geometry, because essentially the applications that I have in mind are applications to the theory of supergravity, which requires speaking a little bit about spin geometry. Anyway, that's the outline, and I called it 0, 1, 2, 3, but it's 4 lectures. I'm not sure each one is one physical lecture, but hopefully in the first 4 lectures I will cover that theory. Let me tell you some references. Unlike Paul, I didn't travel with the books, or rather I traveled with the PDF versions of the books, not the actual books, because, I'm too old to be carrying stuff around. But basically, these are the books that I like. Things that I found useful in discussing these topics. So, this book of Bröcker and Janisch, I have it in German, but I think it's been translated to English. It's called Introduction to Differential Topology. I like it very much. It's very thin. It is a good introduction to differential manifolds and the different ways of discussing objects in differential manifolds. They have 3 ways of looking at things. They have the way the algebraist might look at it, the way the geometer might look at it, and the way the physicist might look at it, which I think for mathematicians is a very enlightened approach to doing mathematics. Then there's this book of Manfredo do Carmo on Riemannian geometry, which was originally in Portuguese, but now has been translated to English. And that's a very, very good book on Riemannian geometry. It's very simple. Everything is done carefully. A more advanced book with lots and lots of material, even though the book hasn't changed drastically since the late 80s, is Einstein Manifolds by Best. Of course, Best doesn't exist. It's a collective of people like Bourbaki, but smaller. It's a very, very good book. Then, if you're particularly interested in mathematical physics, then this book by Schutz, Bernhard Schutz, called Geometrical Methods in Mathematical Physics, actually it's a very nice little introduction to differential geometry and how it's used in physics. And then in particular, the last 2 books are books on spin geometry. They cover a lot of material, but they each have some bits in common, but then they go in different directions. Both are very, very good. I was lucky enough to take a course by Marie-Louise Michelson when she was writing this book with Blaine. So I got sort of first-hand access to the book as it was developed. But it's very, very nice. Anyway, so I'm going to try to, I'll start now. I'm going to try to prepare the notes in advance, and I have it here. Do interrupt me at any moment. I'm happy to answer questions, and I can write, so I can even answer the calculation. Okay, so the first thing that I want to do is to bring everybody to basically the same page, discussing a little bit the basic notions of differential geometry. It's mostly introducing notation and introducing concepts, perhaps in a language you may not be completely familiar with, but that's kind of the idea. So, okay, so let me see if this works. So the basic object here always is going to be some differential manifold, and let's say it's going to be n-dimensional. Is that big enough for everybody to see? Yes? Okay. So the differential manifold, dimension m. If sometimes I might change the dimension. So what is the basic object? I'm assuming you all know what a manifold is, but so basically it looks locally like Rn, and of course, when I say looks like, what I mean is it has a differential structure, and that is something that essentially allows you to determine when a function from m to say the real line is going to be infinitely differentiable, right? So that's the essential idea behind the differential structure. Is just a way to determine which functions are smooth. So we are going to denote C infinity of m to be the smooth functions. Smooth meaning infinitely differentiable. Smooth functions from m to r. What can you do with smooth functions? Well, smooth functions are they are an algebra over the real numbers. So you can do the following to smooth functions. Let me assume that f and g are smooth functions. Then you can add them. And you do this pointwise. So what that means is that the sum at point P is going to be the sum of the values. And you can multiply them also pointwise. Okay. In particular, you can take a function that is constant, and therefore you can multiply by real numbers. So this is a vector space, but because you can multiply functions, it's actually an algebra. This is an algebra over the real numbers, and of course the function that is equal to 1 at every point gives you the unit in the algebra. So when I say algebra, I always mean associative and unitary. I'm not going to say that all the time. So when I say algebra without any other specification, I always mean associative unital. At some point later, when we start discussing Lie algebras, when I say algebra, I might just mean Lie algebra. But for now, let's do that. Okay, so the next thing, next object I want to introduce is the tangent space, which I'm not going to delve too much into it, but well, in fact, the tangent bundle. So the tangent bundle, it's a differential manifold, is going to be the union over all points in M of the tangent spaces. And this is going to be, what is each tangent space? I'm not going to define it formally, but just say that this is the space of velocities of curves passing through P. Space of velocities at P of, let's say, smooth curves. They only have to be one differential, right? Smooth curves passing through P. Okay, so there's a natural map from the union of all these. This is this joint union of the tangent spaces to M. Now, if you have a point in the tangent bundle, it belongs to precisely one of these tangent spaces. And this projection, what it does, it tells me which P, right? Does this work? So which P? Yeah, okay. So which P? Which TPM? It gives P wherever the object is in one of the TPMs, and it just gives the value of P. That's what I mean. So this is natural projection. The next thing I want to introduce are the sections of this bundle. So the sections are going to be, let's see. That's right. Yeah. So sections are going to be maps, smooth maps from M to Tm, which have the property that they assign to every P some vector tangent to P, and it does so in a smooth way. So typical section is, I'm going to call it X. So these are the so-called vector fields. So X of P is some tangent vector to P, and this function depends smoothly on P. So this is called a vector field or smooth vector field. And I'm going to introduce the notation, this calligraphic x of n, to be the set of smooth vector fields. So one thing you can do with vector fields is you can take derivative along the vector. You can take at the point P, you can take the derivative of a function at that point in the direction of that the vector field is pointing at that point. So they give derivations of the. So one algebraic way to think of the vector fields, these are the derivations of the algebra of functions. Derivation just means things that satisfy the Leibniz property. So for example, suppose x and y are such things. So suppose f is some smooth function, let's say 2 upon g and f. Then x of f is going to be a smooth function, which essentially, what function is it? Well, what is it at the point P? It's going to be the directional derivative of f along the value of x of p. But these are derivations in the sense that they satisfy the following properties. So they're additive. So how does it differentiate a sum of functions? Well, it's the sum of the derivatives. But it also satisfies, and that's why it's a derivation, satisfies the Leibniz rule. So it's going to be f x of g plus okay, is that hopefully? Please interrupt me if you have questions. Okay, dual to the, okay, well, sorry, before I do that, let me introduce something, because since we're talking about the algebras, I can already tell you, give you a bracket here. So if x and y are vector fields, let me define the bracket xy as a vector field. And in order to determine what it is, all I need to do is act on a function. And then by definition, the bracket of x and y acting on a function is going to be the vector field x acting on the vector field y acting on the function, minus the other way around, so y acting on. So remember, f is a function, x of f is another function, and therefore y of that is another function. So this is the difference of two functions. So what does it satisfy? Well, clearly from the definition, this is antisymmetric in y and x. So the main properties is one, the fact that xy is minus yx. And the second one is the Jacobian entity, namely x. You nest the brackets and you cyclically add the other two terms. So x, y, and z cyclically in x, y, z. It's equal to 0. So this just follows easily from the definition. So it's a good exercise for you to do. You haven't done this. So what this says is that the vector fields formally algebra. So this forms a Lie algebra with respect to this bracket operation. Of course, it's an infinite dimensional Lie algebra. It's not like the ones that Paul has been talking until now, but it will be more like the ones Paul will talk about later. So it's infinite dimensional. But one thing we'll see is that despite the fact that it's infinite dimensional, once we introduce additional structure on your manifold, for example, if you put a metric, then we'll be able to cut this down in size to consider interesting finite dimensional subalgebras of the vector fields. So let me just say here, so a preview of what's going to happen. It has interesting finite dimension these subalgebras. But we'll do that a little bit later. Okay, any questions so far? Yes.
What are the parameters of this Lie algebra?
The parameters. locally, okay, very good question. Let's do that. So locally, how do you describe a vector field? So you introduce some local coordinates in your manifold. So suppose you have so suppose that these are local coordinates. So from some open set to Rn. And then a typical vector field X is going to be something that looks like, I'm going to use Einstein summation convention. So hopefully, so it looks something like that. Thinking of them as derivations of the algebra of functions, derivations are first order differential operators. So it's going to be a first order differential operator. Well, what are these x mu's? X mu's here, well, these are smooth functions from U. So they're functions, they take little x and the x mu of x. So locally, they are parameterized by all the smooth functions in the neighborhood of where you are. So it's huge. I mean, it contains all the polynomial functions, all the exponential.
The coordinates shouldn't be going to the manifold instead of Rn?
No. The coordinates. So you're thinking about parameterization.
Oh, the other way around.
Coordinates go from the coordinates is a way of assigning coordinates. So
okay, so you use
n tuple of numbers to points in the manifold.
Okay.
You can think about these maps happen to be invertible, so you can always parameterize the points in the manifold using the coordinates. So that's a parameterization. So parameterization goes from Rn into your manifold. Coordinates go from the.
So these these vectors are in Rn.
Which vector?
Like the partial derivatives are in Rn.
Yes, this is acting on functions of the little x's. So okay, maybe I draw a picture. So here's the manifold, and here's a little open set. Then you have these coordinates x mu, which map to Rn. So if you have any function from your manifold to R, you can of course always get a function from Rn to R by simply follow the given a function, because this map is you can always this map is invertible, so you can always break this function into the map x and then some other function here. So this function, once you've chosen local coordinates, has the same information as some function from Rn to R. And this ddx mu's, what they do is they're acting on those functions from Rn. So it's a little bit of abusive notation. I should probably have some push forward somewhere, but if you don't mind the abuse. Essentially, what these coordinates allow you to do is to transport everything that is happening on the manifold locally to Rn. And in Rn, you're working with nice functions of n variables, which are infinitely differentiable, and derivatives with respect to these.
I have another question. The fact that this infinite dimensional algebra is a Hilbert space, does it have?
It's not a Hilbert space. It doesn't have to be. No, Hilbert space would. No, I mean, Hilbert space is a infinite dimensional vector space with an inner product and complete. I'm not talking about completeness here. In fact, it's just an infinite dimensional algebra. If you're in a compact group and I mean, you can give it more structure, but in general, on a manifold, that's okay. Any other questions? Okay, let me then introduce sort of a dual to. So let me put a line through this. Let's continue. So this is kind of. Oops, sorry. So let's. Let me go on and introduce now. We have defined smooth functions, vector fields as derivation of functions. Now we want to introduce sort of a dual to that, which are the one forms. So we consider now the cotangent model. Oops, the cotangent model. So this is the union of, again, this joint union of all the dual to the tangent spatials. So TPM star, these are the linear functions from TPM dot. And similarly, being this joint union, we have a map down to M that just tells me P. It gives me P, which TPM star you are in, and it just gives you P for that. So, and we can discuss sections of that. So we call it alpha. So alpha is going to be a smooth section of the cotangent model, so it's something called a one form. Locally, if you want, in local coordinates. So local coordinates. Well, okay, maybe I tell you how they were defined, and then I can then tell you why they look like they do in local coordinates. So one form. So what is it going to do? This is going to be a function from vector fields into the smooth functions. So if x is a vector field, this one form active on x is going to be a smooth function. Okay. In particular, there is a way of going from, let me call it D, from smooth functions to one forms. The space of one forms, I shouldn't give it a name. I'll call it omega 1. Okay. There'll be more omegas coming. So this gives me a function. You give it a function, and it gives you a one form called df. And how is df defined? Well, df is defined so that if you act on a vector field, it gives you the derivative of the function along that vector field. And from that, you can then deduce that in local coordinates, typical one form, again using Einstein convention, is going to be some alpha mu. And then the derivative is d that I just introduced of the coordinate function 6. And then the idea is that if x is something that looks like x mu dx mu, then alpha of x is going to be simply alpha mu x mu. Summed over mu, but I'm not writing the sums explicitly. Right. Okay. Any questions on that? Right, so we have, let me draw another line to this. We have a Lie algebra, which is the Lie algebra of vector fields. And Lie algebras like to act on things, so we have representations of that. And there are many, many geometric representations of Lie algebras. And they go by the names of the algebra acts by something called Lie derivative. So let's talk about You can see that I haven't used this very much yet. We'll get better as the lectures progress. So let me do it. So these are actions of the vector fields on geometric objects. We've already met one, well, two actually. E.g., for example, we can act on smooth functions, and that was kind of by definition. So x f goes to x. And we've also learned how to act on vector fields. That's the adjoint action that Paul was talking about in the context of finite dimensional algebra, but here works the same way. You take a vector field and you go to the bracket x with y. And what do these things have in common? Well, these things have the following in common. So first of all, let's introduce some notation. So let's call these always by the same notation, L sub x. So that's the Lie derivative along x. Lie derivative along x. And in this language, Lx of f is x of f, Lx and y is bracket x1. Okay, one thing that these Lie derivatives have in common is that they obey the following. This you can check just by almost by definition in these two cases. So if I take the commutator, so this bracket is now the bracket of the commutator of operators. So this is by definition, by definition, Lx Ly minus Ly Lx. This is L of the Lie bracket of x and y. And that's a good exercise. You can check this on functions. That was the definition of the Lie bracket of vector fields. And then you can check this on vector fields, and that's a Jacobi identity. But the beautiful thing about that is that if you know how to act on functions and you know how to act on vector fields, you can act on pretty much any other geometric object by a kind of Leibniz property. So, so how about on one forms? Let's say alpha, which is a one form. Okay, so we would like to understand what is the Lie derivative of a one form along alpha. And what I tell you is that you already know how to do this because of this Leibniz property. So let me explain. Consider alpha acting on some vector field y. That's a differentiable function. So in particular, I know what Lx of alpha of y is. This is, on the one hand, is going to be x acting on alpha of y. Now comes the idea. The idea is to use the Leibniz property. And what does it mean, the Leibniz property? It means that whenever Lx sees anything, it will go and act. It satisfies the Leibniz property. So kind of Lx will act on alpha, and then it will act on y. And if there were there were more things here, we'd just act on every single one of them. So let's do this. So the Leibniz property, kind of internal Leibniz property, I guess we will call it, is the following. It says that this guy, Lx of alpha of y, is actually going to be Lx alpha. First you differentiate alpha and act on y, plus alpha acting on the derivative of y. So these two things are the same. But you know what Lx and y is, because we've defined that previously, and we know what this is. And therefore you can read off what that is. So from these two, you see that Lx alpha, it's the one form such that when you act on y, it gives you x acting on alpha y minus alpha acting on the bracket, which is Lx1. So this is the so that we just derived using this Leibniz property. And you can keep doing this for other objects. For example, let's introduce some more objects. So let's look at metrics. We're going to be doing a bit of Riemannian geometry, so we're going to introduce a metric. So what is a metric? A metric is a smooth family of inner products on each tangent space. So, so this is basically for every point in the manifold, a metric is going to give you some symmetric bilinear form on the tangent space, but it's non-degenerate. And of course, in physics, we don't need this thing to be strictly positive definite, because we'll be most of the time doing Lorentzian metrics, but anyway, so non-degenerate. In local coordinates, we write G as G mu nu, dx mu, and this guy here is symmetric. Okay, right. So, so what does that mean? It means that G is a machine that you feed it two vector fields and you get a function. And it's a symmetric machine and it's non-degenerate in the sense that if for a given x, this is 0 for all y, then that x has to be 0. Anyway, so so now let's compute, for example, what is the Lie derivative of a metric? Well, we again use the Leibniz property. So if you now act on two vector fields, right? So it's again some sort of symmetric a linear form of vector fields. So this is going to be, well, x acts on the whole thing, x, y, z, minus then x, oops, x acts on y, and also x acts on z. And I'm already using the fact that the Lie derivative on vector fields is the Lie prime. Okay, so you get this action. It's good time now to define one of the basic objects in these lectures, are so-called killing vectors. So a vector field. Let me give it a different name. So x, y, they're generic vector fields. But whenever I introduce vector fields that satisfy some properties, I give it some other name. So if you don't mind, I'm going to call it psi. So a vector field psi is said to be killing. And killing has nothing to do with killing anybody. Just killing, it's the name of killing. So I once wrote a grant report called "Killing Superalgebras in Supergravity," and I had a disclaimer saying that no superalgebras had been hurt in this research. But anyway, I don't know how funny they found it, but I thought it was. So a vector field is said to be killing if it annihilates the Lie derivative of the metric. So this is a property with respect to a metric, right? So once you give me a metric, what is a killing vector field? A killing vector field is one that annihilates, whose Lie derivative annihilates the metric. And from the previous expression, we can see that what this means is that C on G of x, y, okay, what is that? It doesn't matter, x, y, is going to be the same thing as G of Cx y plus G of x C point. So remember this because it's going to appear a lot. And we're going to, a little bit later, we're going to learn a different way of analyzing this equation, which actually allows us to really be able to determine, for example, what are the killing vector fields of a certain geometry. Okay, any questions? Good. Okay, so moving right along. So now we're going to talk about how we're doing for time. Okay, let's talk about connections. So what is a wow, it took a long time. Something happened, I mean, just very slow. So what is a connection? Connection is a way to differentiate geometric objects in a way that doesn't really depend on the coordinate system. It's a coordinate-independent way of taking derivatives. So let's first of all talk about linear connections, by which I mean things that allow me to differentiate vector fields along another vector field. Now you might think, well, we already have a way of the differentiating vector fields. We learned about this Lie derivative. The Lie derivative doesn't quite generalize the, what we want to do is to generalize the notion of taking a directional derivative. And what do you know about directional derivatives is that the directional derivative of some object only depends on the value of the vector that gives you the direction at that point. Whereas the Lie derivative doesn't do that. The Lie derivative actually, if you're taking the Lie derivative of y along x, you will need to know how x behaves not just at a point, but in the neighborhood of the point. So that's why we need connections. So linear connection. So the notation is we're going to call nabla. So what this is essentially a way of, okay, you give me, remember, tangent vector. I can think of this also as a vector field, but it turns out to be a map. You give me two vectors, x and y, points in Tm, at the same point, I suppose. And what you give me is another vector, which is the covariant derivative, that's the usual name of this. Covariant derivative of y along x. Okay, so what does the covariant derivative have to satisfy? So it has to satisfy a number of properties. It's a derivative, so it's linear. It has to satisfy kind of a Leibniz property. But the important thing is that it should be, if you wish, tensorial on x. So it only depends on x at a point. You don't need to know what x does in the neighborhood of a point. To evaluate this at a point P, all you need to do is to know what x at P is. Y, of course, you're differentiating. So y you need to know what happens around P, but for x it's not necessary. So formally, the properties are the following. So okay, so nabla x. First of all, it's additive. So this should be nabla x y plus nabla x z. It should obey a kind of Leibniz property. So if f here is a smooth function, this is going to be x differentiating the function times y plus f nabla x y. And finally, if you multiply x by a function, then the function comes out. And that's the important thing. So this thing says that nabla x y at P only depends on x at P. Unlike, by the way, x, y, the bracket at P, which depends, which depends on how x behaves in a neighborhood. Okay, so let's make this more obvious. For example, if I do fxy, this is going to be f of xy, which is what you would like, but unfortunately there's a correction. You have minus y and x. And therefore, this means that this doesn't just depend on x at the point P, because imagine you have a function f which is equal to 1 at P. Then if this only depends on f of x, therefore has the same value as x at P, because f of P is 1, but it gets differentiated. So therefore, this depends, x depends on the neighborhood. So, this would be a covariant derivative or a connection, a linear connection on vector fields. We can extend notationally, by the way, on functions, and we're always going. This is just notation. There's nothing deep here. Just notation. Is that we call this just the action of the vector field of the functions. But the beautiful thing about this is that now, just like we did with the V derivative, by using this Leibniz property, we can find out what the connection does on other objects. For example, on a one form. So again, as for the V derivative, the Leibniz property. Oops, Leibniz property gives nabla x on other objects. For example, we can take a one form. So what is the covariant derivative along x of a one form? Okay, it's a one form, so we need to know what it does on a vector field. And again, we're going to use the Leibniz rule. It says that this would be nabla x on alpha of y minus alpha on nabla x of y. And we know, by the way, what the first term is, because alpha of y is a function, and nabla x on a function is just x on alpha of y. And the other thing is whatever it is. I mean, that depends on the connection. Okay, just one more for good measure. What about if G is symmetric? Well, what is the covariant derivative of x along a metric? Well, a metric, you need to know what it does on two vector fields. So again, we do by Leibniz. So this is going to be nabla x on G applied to y and z. But that's a function, so it's x on G of y, z. Minus the bits, so g on nabla x, y, z minus g on y nabla x, z. Okay, it's a good time now as any to define the notion of a metric connection, which is one where the derivative of the metric is 0. It's kind of like, you know, a Killing vector is one whose derivative of the metric is 0. A connection now, a nabla, so it's said to be metric if the so this is metric, it's just the name. Metric here uses an adjective, not a noun. So nabla is metric if this is 0. And from the previous formula, which unfortunately, the bad thing about not having boards is that I can only have one slide on at the same time. But if you remember, and if not, well, I'll just write again. If you, okay, let's very quickly flash it back. So, so if nabla x is 0, then the right-hand side has to vanish. So you can write this as, you can write it as follows. You can say, well, i.e. x acting on g of yz is equal to g of nabla x, y, z plus g of y. This is true for all x, y, z vector fields. Okay. Notice, by the way, that the Leibniz property of the connection, namely this one, the discrepancy from it being linear in the functions is this term. But this term just has the action of x and f and y. So this term doesn't know anything about which connection I used. In other words, for any connection, this term is the same. So what that means is that the difference between two connections, those terms will cancel, and hence you get something which is tensorial. So one observation, is that if nabla and nabla prime are linear connections, the difference, nabla minus nabla prime, let's call it an x. Well, sorry. I believe this is a tensor. Tensor just means that it's linear over C infinity event. So what does that mean? It means that this guy, let's call this tensor K. So it means that Kx, y, is tensorial. So if I put an f here, this is f of kx. Okay, so what is kx, by the way, is what I call nabla x minus nabla x prime. So what does that say? It says that you have many connections, because if you give me any connection, any other connection is going to be is going to be that one plus some tensor. If you wish, a 1-1 tensor, something you feed in a vector and it gives an axon. So not a 1-1 tensor. One form with a morphism. So 2-1, 1-2, I don't know, 1-2 tensor. Anyway, doesn't matter, but it's a tensor. So that means that the space of connection, by the way, is an infinite dimensional affine space. It doesn't have, there is in general not a privileged connection. But once you give me one, any other can be obtained by adding a suitable tensor to it. Okay, right. Any questions? Okay. Right. There are a couple of natural tensors associated with a connection. So one is the torsion tensor. So what is that? So let me call it t of x and y, and that by definition definition is nabla x on y minus nabla y on x minus the Lie bracket xy. Oops. You can easily, from the properties that this connection satisfies, verify the following. Namely that, well, first of all, this is a vector field. So this is something that gives you, first of all, it's skew symmetric. And then, therefore, you can, it's enough to prove that it's tensorial, it's enough to look at one slot, because the other one, you know, the same the symmetry, so that F comes out. And the definition that goes along with this is that a connection is said to be torsion-free if the torsion is zero. Oops. Now, what does it mean that the torsion is zero? I.e., it means that the Lie bracket of any two vector fields, which has no information about the connection or anything, can be given in terms of the connection as this expression. It's taking a long time to. I'm having the same problem Paul was having. So should I just wait or should I reconnect? You can try and reconnect. You think that's the best way? So disconnect and reconnect. Is that what you're saying? Yeah. All right. Please let me know if it goes funny again, because I'm not always looking at it, and it's difficult. Okay, right. So now comes the fundamental theorem of Riemannian geometry. So pay attention. Okay, so this is called the fundamental theorem. It's really a lemma. I mean, it doesn't allow you to do much except tell you what is the object that you should study. So the fundamental theorem of Riemannian geometry says the following. Somehow it just doesn't react in time. Even though I lock the screen, so I'm locking the output, but it just came out. It's kind of takes a while. Nobody else is using it. Maybe there's interference. Anyway, don't log into the. Okay, so what is the fundamental theorem? It says that. Oops. Suppose that you have a differential manifold with a metric. So that's known as a. I mean, you don't see it, but. Maybe I continue. Oh, so I see it's lagging. So suppose Mg is a manifold with a metric, so-called Riemannian manifold. By the way, when I say Riemannian, some people, when they say Riemannian, they mean strictly Riemannian, meaning that the metric is positive definite. I don't do that. When I say Riemannian, I just mean a metric, non-degenerate, but any signature. So there is a unique metric and torsion-free connection. And what that means essentially, I mean, this is a meta-mathematical statement, is that the study of Riemannian geometry is really the study of this connection. And in particular, being a connection, well, it has a torsion, but it's torsion-free, so the torsion is zero. But as we will see, it has another tensor called the curvature. So a lot of Riemannian geometry is studying properties of the curvature tensor of this connection. Yeah, it has a name, by the way. It's called the Levi-Civita connection, or the Riemannian connection. Or sometimes Riemannian connection. Right. So there's a formula. I'm not going to derive it. This is one good exercise for you guys to do. There's something called, for example, the Koszul formula. and then I'll give you one in coordinates in case you want to do it. So it's given by the Kosovo formula. So what do I need to tell you? I need to tell you to derive the to define the connection, right? I'm at the bottom of the page. Okay, let's do it. So I need to tell you what that is. That's a vector field. But because I have a metric, it's enough to tell you what the inner product of that vector field is with any other vector field. That also defines it. So I need to tell you what this is. And the Kosovo formula is basically a formula for that. And the Kosovo formula says that, well, twice that, there's always a factor of 2 here. So twice that is given by x. So the derivative of g applied to yz, and then derivative along x, and plus y has to be symmetric in, well, ignore that statement. Those 3 terms, and then I should have left some room for the other ones. Let me see, minus g of x, y, z, minus g of y, x, z, plus g of z, x, y. So that's a Kosovo formula. You can derive it quite easily from the 2 conditions that it's metric and torsion free. But in order to do that, there's some combinatorial trick. So what you have to do essentially is to look at, for example, the metric condition for x, y, and z, but also for y, z, and x, right? And also for z, x, and y, and add them 2 with one sign, 1 with the other sign, using the torsion free condition, and at the end of the day, you end up with that. And the reason for the 2 is because basically you'll end up with 6 terms. 2 are the same, it gives you the 2, and the other 4 cancel pairwise. And then you end up with that. So it's really a trivial thing, it's just one of those things that you have to see once in your life. So that's a good exercise. Let me tell you in coordinates how it looks, because sometimes, not everything, but sometimes in coordinates. So, connections in coordinates. That's what the last thing I'll do in this first hour. Very good. So, so what is a connection? Remember, a connection is something that if I give you 2 vector fields, it will take the derivative of one vector field along the other. So let me take for these vector fields coordinate vector fields, namely local coordinates. So let me consider the covariant derivative of the coordinate vector field ddx mu along ddx mu. Well, what is that? Well, it's a vector field, so it's going to be some linear combination of the coordinate vector fields. And that linear combination is going to be called this gamma, capital gamma of mu nu rho, ddx rho. And these things are called the connection coefficients. For the metric connection, for the Levi-Civita connection, they're also called the Christoffel symbols. But, okay, we can therefore write the Levi-Civita connection. Well, we can write the Christoffel symbols for the Levi-Civita connection as follows. So for this one, the Levi-Civita connection, gamma nu rho is going to be 1/2. That's the 2 that we had before, because remember, it's twice the connection what we have. So the connection is 1/2 of the other stuff. And you see, the beautiful thing about these coordinate vector fields is that the Lie bracket commutes, right? ddx mu commutes with ddx mu. So any term that involves the Lie bracket, it's absent. So you only get the first 3 terms. And the first 3 terms actually looks like this. I'm using shorthand notation. Partial mu means ddx mu. I just want to write something. Notice, by the way, that gamma mu nu rho is symmetric in mu and nu. In fact, that's the same thing as the torsion-free condition. If you go back to this definition there, torsion-free says that that minus mu and nu interchange is the Lie bracket of those two vector fields, but that's 0. So that's the same thing as saying that the capital gammas are symmetric in mu and nu. Okay. So now, in the last 3 minutes, let me tell you the how to rewrite the condition that a vector field is killing in terms of the Levi-Civita connection. So, okay. So we have mg, this guy, the Levi-Civita connection, and suppose that this guy is killing. So remember, what did it mean to be killing? Killing meant that the Lie derivative of the metric along C is 0. But that also had there was an identity that we how do you say that we derived based on what the Lie derivative of a metric looked like, and that identity was the following. It said, let's see, if I differentiate. If I differentiate the inner product of x and y, which is along with a metric, which is a function, that's the same thing as g of so this is y plus g of x c. But now, because I have the Levi-Civita connection, I can use, you see, I can think of this guy here. This is the same thing as the covariant derivative along C of the function gxy. And this, by Leibniz, I know what it is. Well, it's going to be the Lie derivative of every object that it meets on the way. So the metric plus metric plus x. But of course, this is 0 because this is the Levi-Civita connection and it's metric. So what we find is that this, which is these two terms, are equal to these two terms. But you see, the connection is torsion-free. So now, using the torsion-free condition, you can write, for example, using torsion-free, let me write it. So what is this term here? For example, using torsion-free, that's going to be nabla x c plus cx. And similarly, this guy here is going to be nabla c. Sorry, nabla y c plus cy. And now let's compare this line with this line. So you see, they're equal. So this term here has two terms. This guy plus the Lie bracket term, but the Lie bracket is exactly that, so they cancel. And similarly, the Lie bracket term here and the Lie bracket here cancels. So what you're left with is the fact that C is killing if and only if these two terms with the first two green terms here is equal to 0. So the conclusion is that this guy is killing if and only if g of nabla x c y plus g of x c y. Sorry, the other one. Y c is equal to 0. So that's called Killing's equation. Not to be confused with Killing's identity, which do a little bit later, which is a consequence of the solution. So let me write it down. This is called. So let me tell you what it is in local coordinates. It's very simple. So in local coordinates, basically this says that if I take, now I'm going to use shorthand. So nabla sub mu is going to be by definition nabla along ddx mu. Right? So this says that this plus nabla So what I've done is I've used the metric to lower the index of, so the vector field normally has the index up, but I use the metric to lower it. And this connection kills the metric, so I can do it before I apply the derivative or afterwards. It doesn't matter, so that's what I get done. Okay. I think we'll take a break, or how does it go? Peter, do we take a break, 5 minutes, and then continue? Or?
As you prefer.
I think so, yeah, just because, well, this is a natural breaking point. So
Okay, let's take it.
okay, all right. So in 5 minutes we continue. So I can, I'll turn this up. It's okay. I'll give this, I'll send this to you, and then you can, I can output these things. And you can make them available.
Anybody who wasn't able to receive the notes before, can you tell me what format? I'm not sure. I can say
How is it?
It's fine. Yeah.
How is it?
It's just that it lags a little bit.
Yeah, no worries.